Hello, my name is Robin Shakya, and I'll be presenting on wireless power transfer.
Wireless power transfer is a technology used in electrical engineering that allows electrical energy to be transferred from a power source to a device without the need of physical wires or contacts. The energy is transferred through an electromagnetic field which is created between the transmitter and the receiver. The basic principles of wireless power transfer are based on the laws of electromagnetic induction. The transmitter coil generates an alternating current that creates a magnetic field. The magnetic field then induces a current on the receiver coil, which can be used to power a load, such as a smartphone or an electric vehicle. Some common methods of wireless power transfer include radio frequency waves, which is a very common method of transmitting data, as the waves can propagate through vacuum. RF waves are also used to transmit power in microwave ovens. Optical links uses the light, such as ultraviolet or visible infrared light, to transfer energy between source and receiver over long distances. The receiver in optical link could include photovoltaic converters, solar cell, or a photodiode. Ultrasound has also been applied in low power data transmission. Capacitive power transfer uses time-varying electric field between capacitor electrodes to transfer power wirelessly. Capacitive power transfer has been applied to low power and data transmission systems such as biomedical implants, bioinstrumentation, integrated circuits. Inductive power transfer is a method that uses time-varying magnetic fields between mutually coupled coils to transfer power wirelessly. It is very popular and is used in most of our consumer electronic devices, such as smartphones and electric vehicles. Electromagnetic induction serves as the fundamental law of wireless power transfer. So Faraday's law states that when a conductor is placed in a changing magnetic field, an EMF is induced in the conductor, which creates an electric current. Mathematically, it is expressed as the rate of change in magnetic flux. The negative sign in the equation indicates that the induced EMF is in the direction that opposes the change in the magnetic flux. The power transfer in an inductive wireless power depends on several variables, including coupling coefficient between the transmitter and receiver coil. A higher coupling coefficient leads to a higher efficiency of power transfer. The distance between the coil also affects the strength of the magnetic field and the amount of power that can be transferred. As the distance increases, the power transfer efficiency also decreases. The size and shape of the coil can also affect the strength of the magnetic field. Larger coils generally produce stronger magnetic field and can transfer more power. The frequency of the AC also affects the efficiency of the power transfer. Resonant frequency of the coil should be matched from maximum power transfer efficiency. The impedance of the load connected to the receiver coil affects the efficiency of the power transfer. The load should match to the receiver coil for maximum power transfer. Environmental factors such as the presence of metal objects or other materials that can absorb or reflect the magnetic field can also affect the efficiency of power transfer.